Good morning, good afternoon, and good evening, wherever you guys are joining from. Have the pleasure of speaking to Mr. Manjunath Rao and Dr. Shankar here. And today we'll be discussing on the impact of sustainable solutions and primarily from an engineering standpoint, and how the life cycle of a plant can be sort of looked at in terms of where we can add value. So. As part of this discussion, I'll be sort of hearing from Mr. Manjunath and Dr. Shashank on Shankar on a bunch of interesting use cases from their experience, as well as points on how we can sort of bring these interesting solutions together to see how these outcomes can come about, right? So I'll start with a quick context in terms of why we're doing this and how this comes together, and and so we hear a lot on, let's say, target net zero, and companies putting up a lot of their uh, like sustainability targets, and also even, let's say, countries, for example. But as of today, when we look back and sort of uh, look at the sort of progress that's been made, right? Of course, there's been very interesting solutions that have come about, but we're absolutely nowhere near the sort of track on where we should be to reach net zero by, let's say, in some cases, 2050. And so in that case, for example, this interesting report from Accenture talks about how, let's say, just 18% of the overall companies globally are on track to achieve their net zero goals by 2050, in the next 25 years or so. And and if you look at, let's say, uh, meeting their targets from today, unless they sort of uh, double down on their sort of activities to sort of look at energy and emissions and all of these areas, there's no way this is possible, right? So we really need uh, path breaking scenarios. We really need sort of scalable solutions and not just point solutions, and that's where it'll be interesting to hear from the folks here to sort of map them against industry specific needs. And yeah, and what you also see is, let's say, goals from the United Nations sustainability development standpoint, right? So on how things come together at a global level, and very interesting statistics here on how, let's say, the the energy consumption with respect to CO2 emissions and all of these areas for different industries. And you see the different industrial processes, as well as the production of different areas for these particular processes and these industries play a big role in terms of the percentage, right? So in this case, let's say 40%, 45% of the energy consumption, for example, in the overall scheme of things from an oil refining standpoint, a lot of it goes into the production of refined fuels. And similarly, when we look at other areas of gas processing, steam methane, steam cracking, and on the other areas, of course, it is a different scenario with chemicals. But when we look at, let's say, the CO2 emission standpoint, uh, more than 25 to 30% of the overall emissions percentage still boils down to, let's say, steam generation and other areas of, let's say, heat integration, apart from what we typically look at energy as electricity. So there's more to this whole thing than just electrical energy, and that's where we'll be looking at how we will sort of leverage on some interesting concepts to arrive at how we can look at energy from a different standpoint. So just to sort of bring this together, like Utthunga in partnership with GyanData here, we've been looking at sustainable solutions from different focus areas. So this is where we're looking at energy management, reliability, emissions management. Of course, there's an aspect of safety and security, and finally, very interesting engineering solutions for green energy, right? And and the basis for all this, in fact, the high impact areas is what we call it, from the energy management, is what we're going to talk about in a little more detail. So what I would first like to sort of uh, double down on and understand a little more is the area of energy management, as where the aspect of energy assessments and audits comes about, right? So, Mr. Manjunath here, from his experience, of course, we would like to hear on what this phased-wise approach is. How do you guys go about doing this? What type of, let's say, tools and engineering activities are involved? And yeah, this will help us understand a little further before we go into more on how do we optimize things.
Yeah. Thank you, Nitin. I hope I'm audible. Now, see, energy, when we are talking about energy, this one, energy consumption patterns, energy, the generation, energy consumption was from long, long before. Everybody was talking about energy, energy consumption, and how to optimize the energy and all. But where was the eye opener for us was in the period of COVID and some war situation in Europe. So then only the people started talking about how to conserve the energies very strictly and to go towards the net zero. And see what we foresee in the industry, it is not only electrical energy. The people, when we talk about energy, the people talk about electrical energy, but it contributes only 8%. But for electrical energy, there are many other factors contribute that we have to differentiate. And second thing, there are thermal energies, even water energy, internal energies. Every energy is a part of it. That is what it makes a big chunk of the energy system in our oil and gas and petrochemicals and chemicals. See, oil and gas is a highly matured in the sense of energy because do energy, they generate energy and they are accountable for energy consumption also. Okay, but there are the oil and gas are all big players. They know how to do it. They know how to get the data. They know how to optimize it. These are the simple factors they are getting into practice, and they are making it. Where comes petrochemicals and chemicals? Petrochemicals and chemicals, mainly there are the petrochemicals are, maybe I can call it, is in a middle investment. This one, yes, they do have some policies to do a lot of energy conservation, energy management, and all they can put it in. But comes to chemicals, there are huge amount of energies, energy things because the small the as the industry into split into very very small sectors, it is difficult for them to do energy management and energy this one. But we are coming up with a simpler approach for them to do energy management and energy sectors in a simplest way. See, we are not here to shift the energy from one phase to another. The second is the only our aim is to decarbonize. That means shifting the main fuel energy into the renewable energies, other forms of energy. Because see, if I'm shifting from one place to another, one form of energy to another, the carbon remains same. So this is what we are doing it. Second is we do in systematic. The energy management need to be done in a systematic manner. See, there are many, 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 many players in this world. They come up, they say we do energy management. Once they do energy management, they look at the LED bulbs and some other sort of bulbs, electricity and other. This is what we are not looking for. We look for all type of energies, and its conservation. The main thing what we are doing it is how we do this energy audit. We split into four phases. One phase we collect only the data, relevant data, and we analyze which are the energy guzzlers in the industries, what exactly it is doing it, how to convert that energy, whether they are converting into electrical energy and checking, or they're modifying their process to consume reduce energy. This is where maximum amount of energy can be saved. See, I can reduce a little bit of electrical energy, but if I fine tune my process, if I fine tune my process inefficiencies and deficiencies, then we can get a big amount of energy savings here. That is the purpose of this audit. We do it in audit phase and implementation phase. Audit, we do it in four phases. One is phase one. We collect all the data from the end users, or where the energy is consumed. Second line is a baselining. Baselining, see, 30 years old compressors are the 30 years old, 40 years old equipment. Is this the same energy efficiency like when it started? No, we need to start the baselining of each pattern. We use some tools to baseline, and then we baseline according to the industry standards. And we go way in very much in detail, and we do the baselining. That is the most important factor in phase two, is to baselining and benchmarking. So if the benchmarking can be done on the industrial sectors, in the worldwide, how it is happening. At the same time, we do use some calculators and calculation methods and tools to come into benchlining. So phase three is we do real finding the opportunities. We use all type of simulations. We do all scientific methods of simulations, and this one, how to reduce the process energy, how to conserve the utility energies, all type of energy we do with the simulation method, and what exactly we are having ex- against what is the benchmark, this one. So if it is a positive, negative, that is how we do the basically in phase three. Phase four is a conversion of phase three, whatever the opportunities is there. Okay, we convert that. Maybe we have to put energy management, the roadmap for them, how to do it, and what are the energy guzzlers, how we can save, how we can save the energy with a similar investment. See, everybody looks at whether it is oil and gas, chemicals, petrochemicals. Everybody looks at what is the ROI basically. If I invest something, what will be the return when I will get the money back? So these are all the calculations will be done in phase four. So the this all this composite of phase one, two, three, four. It is exhaustive. It is nothing to do. It is an audit, and we find out the audit reports in a proper format, and we give complete information on what is the investment and what is the ROI and other things. Uh, Actually, we were about to do a complete one country's asset that comes offshore, onshore, upstream, downstream, midstream, FPSOs, and chemicals, petrochemicals, everything in a country's asset. We want to do. We were supposed to do in the same four phase wise. It was taking around 3.5 years for only audit purpose. Okay. See, we have started. Yeah,
Yeah, so I
we
think
have started.
if we
Yeah,
look at maybe specific to a plant, if I can understand, uh, when you consider, let's say in this case, like a petrochemical plant that you're talking about, uh, uh, where are the opportunities that you looked at for the areas for improvement, as well as how did you go about defining the energy roadmap, and of course the final ROI and the savings, right? So if you can give us a bit of a deep dive
yeah,
here, that'll be good.
yeah. Actually, this was a very funny situation when we entered in energy management system. We were traveling in the night and we saw a chemical plant. I said, okay, what we can, there was a petrochemical plant. We said, oh, what we can do here. So we made our entry into that petrochemical plant. very nice plant, beautiful, everything was good. And they said to us, what you can do? We said we can do optimization and we can do energy audits. And they said, okay, we have energy audit done by X, Y, Z, all biggies. So we said, okay, you give us one small audit, we will give you a result within few days. Then they allowed us, two, three members of our team, including myself, we went there. Um, they allowed us to go inside the plant to collect the data, and a lot of data were missing. But in the first half of first day itself, I said, guys, you are losing. uh, I can say it is 1.78 crores per month. Um, they were shocked and they said, no, it is not possible. I said, yes, you are losing it. Yeah, then they said to explain, we explained them where was the problem. They were taken back and they asked us to, finish the story and go back. We'll call you once again. When they called us back, there was a lot of change in organizations. A lot of people were removed, and because they were losing it for 25 years. It is unbelievable, this one. So we started the detailed audits as phase one, phase two, phase three, phase four. We found a case where the largest thermic heater was there and it was operating at only 18% of its capacity. And the efficiency, they were claiming 85%. When we checked, it was only 55%. So the efficiency changes from 55 to 85, and it was the largest heat consumer. Heat. Then when we saw that, we calculated, and we found out this was the lapse. It was contributing almost 1 crore per month. The next one was, there were a lot of chillers, water, this one exchanges. It was not monitored well. They did not have proper input, proper measuring points, and they were not knowing how to operate they were not, I don't say they don't know, but they were not concentrating how to improve the efficiency of the chillers and everything. We made a total detailed study within 2 weeks, and we gave them a solution which had only 12 months ROI. Okay, but there was an investment also. So this is how we work in that. We worked towards the electrical energy, HVAC, process optimization, chiller optimization. When you look at that, was the main thing. Process optimization gave us the maximum benefits comparing to any of the energy audits initiative, any of the other forms of energy audit. It had an impact, but when we did the process optimization, the energy optimization came into this one, like the batch reactors ending the reaction time. And if you can reduce the batch reaction by 10% or 15%, the energy saving will be enormous. So these where we concentrated, and we gave them the solution, and it is working properly with that now. Yeah.
Great. Thanks, sir. So, I think what I want to talk next is, okay, from this whole assessment and the whole energy management roadmap that you had in experience to sort of go the full journey. Uh, Aligned with what we wanted to sort of look at from the overarching topic today is also to understand the the uh, the different value areas that engineering can play a role across, let's say, the complete plant's life cycle. So I think understanding the role of engineering and the different activities of engineering across this whole life cycle is key before we double down on especially the area that you mentioned on process optimization, right? So how that can come about. So if you can give us a little more of a brief on this, and I think that will set the tone to move to Dr. Shankar to understand a little more.
Yeah. See, entire life cycle depends upon only one thing. That is how you design your plant. Okay. If the design is perfect, you can go into sustainability in even in the design stages to make the plant life cycle comfortable and long lasting. Why I say is the design is the lot of process engineers are there and engineers are there. They keep up the margins for the designs at maximum. So it is not always good to have a big plant and operate in a smaller size. That's what I explained in the last this one. It was heater was designed for 21 million. They were operating at 4 or 5 million. So it doesn't make any sense. So you have to design it for the fit to that purpose. The design conditions gives us the maximum energy or sustainability value in the design conditions. You can look at the see nowadays there are many simulation tools are there. You just put the in all the cases and find out what is the best and optimum simulation it works for a design. So designing is a main phase. What I say is whatever the energy we talk about. See what we talked about audit and all. When after the design itself, the people will go. By that time, you are losing a lot of energy and cost. So why don't we design energy optimized the process designs for that? For that purpose. Second, once this all comes covered under basic design, basic engineering, then it goes to detailed engineering and to build. Detailed engineering, if you are not concentrating or if you are not looking at in a very positive way, then it can yield in many mistakes in sustainable to get the sustainability in plant life cycle. So I've seen a plants are built haphazardly without scientific this one to save some amount of real estate or some amount of land or some amount of this one. They place they structure somewhere. The orientation is different and a lot of things are coming in while you are building. So when you are building, again, sustainability becomes a main factors. Operations, I just explained how the operations plays an important role. See, in energy, when we go and audit, our findings are like this: 30 to 40% engineering impact, which is happening. Maybe it might have, for many other reasons, it could have happened. The engineering impact on this one, but 60 to 70% it is on operationable. The operation plays a very important role in sustainability. It is not only energy, it is environment, it is waste recoveries, and everything the operation depends. I'll give you an example. They had a chillers. Some people they had a chillers. They were not knowing what is the value of chilled water to the normal water. So they were operating they were using chilled water instead of normal water. The cost impact was so high and the energy impact was so high. So there are many things, control valves operations and lot of logics implementation and unnecessary shutdowns, unnecessary startups. These are all the operational problems which gives the life cycle, plant life cycle in a problem. Even including maintenance. See, a lot of people they do regular maintenance or preventive maintenance. Now the most efficient way of the things are coming in the way of uh, in the way of predictive maintenance, prescriptive maintenance. Lot of thing, lot of subjects are covered inside. We can predict the failures. We can have the logistics in well before, and that is how see, if you are reducing the downtime, that is also directly, that is also directly impacted for the energy conservation and plant life. So the maintenance, if you're making in a sustainable manner, so you will get in the proper life cycle in the plant. So these are the factors which we consider when we are doing even in the design. And now digitalization is driving this sustainability. Again, digitalization also gives an importance for the sustainable engineering and its practices. Yeah.
Great. Thanks, sir. So I'll now jump to Dr. Shankar. So to sort of double down on the optimization area, right? Because the potential for reaping benefits from that is probably immense, like what Manjunath sir mentioned in a couple of use cases as well. So from the plant life cycle standpoint, again, maybe taking the energy, oil and gas specific value chain. Uh, can you highlight a little more on what these optimization areas are, and what sort of impact it can bring about?
Yeah, thanks, Nitin, and thanks to Mr. Manjunath for setting the table. In fact, he touched upon a wide variety of areas by which where energy savings can be achieved, starting from the equipment level, where you can look at the efficiency of individual equipment. You can look at maybe where heat losses are occurring in a plant, look at insulation, things like that, which is good housekeeping practices, what we call good housekeeping practices, which can save you some energy of the order of a few percentage. You're talking about 2 or 3 or 4% change. But he did remark on one thing: the largest gain in energy is going to happen if you make process design changes. I mean, this energy savings, typically it's seen in the past to get you somewhere between 10 to 30% energy savings. If you do an improper design, you could lose as much as 30%. That's the highest. In the late 80s, in the mid to late 80s, there was a technology called pinch technology that was developed to come up with proper process designs. What do we mean by process design? Process design focuses more on the structure of a process rather than the individual equipment. It is an orchestra. You can imagine how music is composed if you have several instruments being played, right? It will be a cacophony if they don't play properly. They have to operate in symphony. Very similarly, a process should be regarded, a process plant should be, which is comprising of several types of equipment, whether it's a distillation column, heat exchanger, compressors, and so on. They have to work in symphony in order for you to produce good music, or in this case, the music is consume least amount of energy, right? I mean, that's exactly where pinch technology comes in, and it can be applied in, for example, in the initial stages of 80s and 90s, they focused on thermal energy usage in a process plant, whether it's a refinery, petrochemical plant, fertilizer plant, pulp and paper, and so on and so forth, a variety of processes. And they showed that by just proper redesigning, because these plants were already designed, you need to actually change, do some rerouting of the piping, maybe add a few exchanges here and there. So it did cost investment, but the payback periods were of the order of 6 months to a year, and the energy savings that you could achieve was the order of anywhere between, as I said, 10 to 30%, purely in thermal energy usage. Now, coming to the last 10 years, the focus has been not just merely on thermal energy usage, but also both thermal and electrical energy usage. How can we look at this combined energy utilization in a process, right? And if you look at it, typically a chemical process, 80% of the energy consumption is actually through thermal energy usage. And only about 20% of the energy usage in a chemical process is from electrical energy, which is used to drive compressors, pumps, and so on and so forth, right? The hope is that if we can shift some of the energy utilization from thermal to electrical, okay, and in a cost-effective manner, mind you, if we can do that, then hopefully we can do what is exactly imitate what's happening in the automobile industry. Can we shift from an internal combustion engine to completely an electrical driven battery operated? It is not possible. I'm sure that in a chemical process, you can't do a whole shape shift, but you can do some of that shift from thermal to electrical. And hopefully, if that electricity is produced from renewable sources, you have a sustainable solution also. Not just a cost-effective solution, but solution. And that is exactly where the pinch technology process methodology has been modified to look at this combined thermal and electrical energy utilization. And I'm going to take some simple examples where this technology can be applied. Here, the first illustration I'm only showing is extremely simple. It occurs in a power plant. You have fuel gas that's coming out, flue gas that's coming out of the boiler, and it contains a lot of energy, and you want to extract it. The way you extract is you transfer some of the energy to heat up the air that goes for combustion along with the fuel, and or you preheat the water that is going into the tubes for converting to steam. So you have two choices. You can use part of the energy to heat up the air and part of the energy to heat up the water. In the left-hand side, the order in which you do the drill. Here, the flue gas first heats up the air and then heats up the water. Okay. If you just simply interchange the order, use the same exchangers. I'm not changing any of the equipment here. Simply decided that water should be heated first and air should be heated next. It turns out that you can actually save 10% energy just by doing this. It's very amazing. It's the same process stream, same set of what you call flow rates. Nothing has changed. How come? What I'm saying is configuration makes a difference, because thermodynamics dictates how much energy you can transfer from the flue gas to the air or water. It depends on the temperature, not just merely on the fact that it's a stream. So simply changing the order, you can show that actually you can recover. And this is a simple thermal process where we are only trying to minimize thermal energy usage. Okay, and this can be applied to any power plant. If you look at the current configuration and say, hey, can I change the configuration and get something out of it? You might find easy, what you call definitely potential savings. This is the kind of savings that you can get from a process design change. And pinch technology is a formal technique, just like an audit process, which tells you where can you achieve it, how much will be the thing, and it allows you to calculate the ROI, payback, and everything. Okay, complete. And it also uses a simulation tool in the process. There are now standard simulation tools which can be used to actually study these kind of things. Okay. Here I'm only talking about thermal. I will actually go on to thermal combined with electrical. And I've taken again the example of a simple distillation where the boiling point difference between the top and the bottom stream is of the order of 10, 15, 20 degrees, let's say. Example, toluene benzene, it's of the order of 30 degrees. You can look at propylene propane, which is less than 20 degrees, and so on. Right? So in these kind of things, what happens, and also some of them operate below the ambient temperature. So you need a significant amount of energy, thermal energy required to supply at the bottom, which is called the reboiler, and take it off at the top, cooling utility at the top to remove the heat. So this is a standard, what is called a standard distillation column, where you supply heat at the bottom, reboiler, and take out at the column. And this requires, the conventional column requires a significant amount of energy, simply because the driving force or the temperature difference between the two components you're separating is not very much, or not significantly high. One can do a very remarkable thing here. We can take the top stream, here the vapor, compress it, and increase its temperature, and then transfer some of the energy to the bottom stream. That is what we call heat integration. In order, you can't simply take the stream as is in the conventional column and do this, because the top temperature is lower than the bottom temperature, and therefore energy will not transfer from the top to the bottom. It's the other way around, right? If you want to make the energy reverse, then you have to heat up the stream somehow, the top stream. And one of the ways of heating is by compression. So increase its temperature, that allows you to transfer the energy and do it. So in this case, what you're doing is you're sacrificing some electrical energy in the process and gaining some thermal energy in the process. This is what I call a trade-off between the two forms of energy. And it turns out this is called vapor recompression technology, and it can be applied to close boiling mixtures, separation of C2 splitting, C3 splitting in refining or petrochemical, even methanol water separation, benzene toluene separation, and so on and so forth. Several different columns. In fact, there are 20 different distillation process where this is a viable technology. What we have come up with is with a complete comprehensive pinch analysis which tells you what's the best you can achieve. How can you achieve this trade-off in an most economical manner? How much energy can be actually supplied by electrical? How much you can actually save as a consequence from thermal? And make sure this is cost effective. And it should pay back for the additional compressor you're going to put in. Right? That's the additional investment cost you're going to put in. And the payback here, we can show it's on order of a few months, 6 months roughly. And I've shown you here a comparison. Today's many of the configurations that are currently prevailing in industry, we have shown what is the kind of operating expenditure they're currently incurring. Whereas if you apply this technology and do a proper design, you can get your operating expenditure to almost half of what's currently prevailing. We were talking about 33% compared to the best in the current operating what I call set of plants. So configuration, again, it is a matter of configuration. You not just heat it. Which one do you exchange with? How much do you split it? All these various options are comprehensively kind of captured in the methodology, and you can actually apply this for saving energy. So this is a simple example where we have actually shown you can do a shift from thermal to electrical and achieve it in a cost-effective manner, okay, and reach your partly your sustainable goals. The assumption is the electricity finally is going to come from renewable sources, which is not happening. Again, if you look at it, again, to give you some idea, India, about 10% of the energy requirements in electricity generation is through renewables. We are talking about hydropower, nuclear, all put together. Only 10% of the electricity generation is from renewables. But hopefully by 2030 or 2050, 30% or 25% of the energy, electricity generation will come from renewables, solar, wind, all put together, right? So I think, ultimately the chemical industry also should do what we call the electrification of the chemical industry should happen, partly shift to it. And there are different processes, sub-processes you can take. I only illustrated VRC. You could do an LNG liquefaction. You can do it in air separation. And you can do it in what you call any kind of liquid air energy storage and so on and so forth, wherever low temperatures and high pressures are both prevalent in the process. And you can actually achieve significant savings, both in terms of operating cost and in terms of sustainability, meeting the sustainability metrics. And I'd be ready to answer more questions, but this is in short what I wanted to actually say about it. Yeah.
No, I think you put it beautifully in the answer in terms of how the chemical industry should gear up for electrification of this whole thing to sort of solve the immediate problems that we can address, right? Rather than waiting for the whole thing to come in from a renewable standpoint and things like that. So there's a lot of things that we can do as of today. So yeah, what we wanted to do is get a perspective of how different aspects of engineering tools, and these new areas like, for example, the pinch technology and these areas that you mentioned can add immense value today to a lot of chemical industries, and I'm sure the audience might have a lot of questions. So what we'll do is we'll get them on comments and of course come back to them if there are any specific areas they're interested in. But yeah, we wanted to have this sustainability series of sorts, starting with a combination of both of you to sort of give us a better context into how things are going about today. And we greatly value your time, and thank you for joining us. And we'll of course come back to you for any specific questions that come in and address them over LinkedIn, of course, to whoever has any specific points there. Thank you, Manjunath sir. Thank you, Dr. Shankar.
Thank you for this opportunity.
Thank you.